finding the Thevenin equivalent. Particularly, we are interested in finding the Thevenin impedance. Okay, so it should actually be Z Thevenin. That's what I should be writing if I am careful. Okay, find the Thevenin impedance Z Thevenin looking into the terminals AB. And then it is given that the frequency of operation is 25,000 radians per second. Well, how do you go about finding this? The first thing we want to do is to write the frequency. Okay, it's to write the um, impedances of the circuit in the frequency domain. Okay, so this one, when you calculate it, is going to be 1 over j omega C1. Let's call this capacitance C1. This is going to be capacitance C2. It will be 1 over j omega C2. Now let's calculate ZC1. ZC1 equals to 1 over j omega C1. Plug in the value for omega, 25,000 currently, and for C1, which is 10 over 3 nano. Okay, so you should see a value of ZC1 equals to negative J 12,000 ohms. Similarly, calculate ZC2, 1 over J omega C2. Plug in the value for omega, plug in the value for C, which is given to be 5 over 3 nanofarads. You should get a value of negative J 24,000 ohms. Now we are ready to write this circuit in its frequency domain. Okay, so all we have to do is to write this guy as a negative J 12,000 ohms. And this guy is negative J 24,000 ohms. That's it. So we have written out the frequency domain equivalent circuit. Okay, now let's see. I'm going to do something really quick here. Let's look at this loop. Okay, let's look at this loop, the left hand side loop. Now, because there is a dependent source, what we want to do is to apply a test voltage and look at the test current, right? That is the method we have been following all along. In order to find the Z Thevenin, what we do is Z Thevenin across AB is V test over I test. Okay, we don't know the absolute value of V test. We don't know the value of I test. We just are interested in this ratio V test over I test. We don't need to know the values for V test and I test individually. Okay, now one thing that we want to notice here is I delta. Okay, I delta is the same as I test, right? Because it's the same current. It's the same current that's flowing through. Okay, it's the same current that's flowing through. Now, what is the current flowing through? Oops, what is the current flowing through this 125 ohm resistance? Think about it. That is 1 delta coming in from here and 19 delta coming in from here. So the current here is 20 I delta. Okay, because there is I delta coming in here, 19 I delta coming in there. Okay, so now we are ready to write KCL around this loop. Okay, so look at this loop. Uh, it is this color. Can we write KCL in that loop? Sure, we can. Let's start at the bottom left corner. I'm going to call this loop 1. Okay, so KCL, I meant to say KVL actually, Kirchhoff's voltage law around loop 1. Okay, start at the bottom left corner. I see a negative V test. Okay, and then followed by plus I test into negative J 12,000 ohms, that is coming from this capacitance. Okay, plus I test, which is the same as I delta, I test into 1 kilo ohms, plus the last component is this guy, plus 20. Okay, I test, which is the same as I delta times 125 ohms. Now, according to KVL, all of that sum of voltage drops around this loop should equal 0. Okay, once you do that, V test, you can factor out V test to the, take V test to the other side and factor out I test. Okay, I test. You're going to see that this is going to add up to 3500. Okay, 3500 ohms minus J 12,000 ohms. Therefore, V test over I test, which is the same as Z Thevenin, is 3500 ohms minus J 12,000 ohms. That's it. So if you are to write this entire equivalent circuit, okay, all of that circuit, A and B, which includes all of these terms, all of that can be written simply as a resistance of 3500 ohms and a capacitance of negative J 12,000 ohms. Okay, so this is the Z Thevenin. That's it, pretty straightforward.